Deep in the outer reaches of our solar system, tumbling through the frozen void around Saturn, there is a moon that defies everything we thought we knew about celestial bodies. It looks like something took a massive bite out of it. It spins in a way that no computer can predict. And when the Cassini spacecraft flew past it, the data that came back left scientists staring at their screens in disbelief. This is Hyperion. And it is one of the strangest objects ever discovered in our solar system. Most moons are spherical, held together by their own gravity into neat, predictable shapes. Hyperion looks like a giant sponge, riddled with deep, dark craters that seem to swallow light itself. Its surface is so porous, so weirdly textured, that standing on it would feel like standing on frozen foam. One wrong step and you might sink into the unknown. But here is where things get truly bizarre. Hyperion does not spin like other moons. Every other major moon in our solar system rotates in a predictable pattern. You can calculate where they will be, how they will turn, centuries into the future. Hyperion refuses to obey these rules. Its rotation is chaotic in the mathematical sense. This means that if you were standing on its surface, you would never know which way the sun would rise tomorrow. The tumbling is so unpredictable that even with our most powerful computers, we cannot tell you which side will face Saturn a month from now. Why does this matter? Because chaos like this is extraordinarily rare in nature. The universe tends toward order, toward patterns, toward predictable rhythms. Hyperion is a glitch in that system. A cosmic anomaly spinning through the darkness of space, breaking rules that have held firm for billions of years. And then there is the question that kept researchers awake at night after Cassini's flyby in 2005. The spacecraft was supposed to pass by at a safe distance, gather some data, take some photographs. Standard procedure. But as it approached, something unexpected happened. A beam of electrons shot out from Hyperion's surface and struck the spacecraft. Hyperion was electrically charged. Powerfully charged. The kind of charge you might expect from rubbing a balloon against your hair, except scaled up to cosmic proportions. The static electricity on this moon was strong enough to reach across the vacuum of space and discharge into a passing spacecraft. No one had predicted this. No one had even theorized it was possible. The leading explanation involves that strange, spongy surface. Hyperion is bombarded constantly by ultraviolet radiation from the Sun and by charged particles streaming from Saturn's magnetosphere. On a normal moon, these particles would hit the surface and dissipate. But Hyperion's surface is not normal. Those deep, shadowy craters trap particles. The porous texture prevents charge from spreading evenly. The result is that electrical charge builds up over time, with nowhere to go, accumulating in the cold darkness until something comes close enough to discharge into. Cassini became that something. It flew through an invisible cloud of electrons streaming from the moon, a phenomenon that scientists now call Hyperion's charged environment. The spacecraft survived, but the data it returned opened up an entirely new field of study about how small, irregular moons interact with their environments. Think about what this means. In the void around Saturn, this tortured chunk of rock and ice is essentially building up a massive static charge, waiting in the darkness like a cosmic capacitor. If humans ever tried to land on it, their equipment would need protection against electrical discharge that could fry sensitive instruments. Astronauts walking on the surface might create sparks with every step, tiny lightning bolts jumping between their boots and the ancient ice beneath. But the mysteries of Hyperion run deeper than its electrical properties. Consider its composition. When scientists analyzed the light reflecting from its surface, they expected to find the usual suspects: water ice, rocky silicates, maybe some ammonia. They found all of that, but they also found something else. Scattered across the floors of those dark craters, there are deposits of material that appears red and organic in nature. Organic material. On a moon of Saturn. Trapped in craters so deep and shadowy that sunlight rarely touches them. Now, we need to be careful here. Organic does not mean alive. In chemistry, organic simply means compounds containing carbon, the building block of life as we know it. These compounds form naturally throughout the universe. But their presence on Hyperion raises questions that we still cannot fully answer. Where did this material come from? How did it get concentrated in those craters? And why does it seem to be most abundant in the darkest, most protected regions of the surface? Some researchers believe the organic compounds arrived via comets, ancient visitors from the outer solar system that crashed into Hyperion and left behind traces of their primordial cargo. Others suggest that compounds formed in place, synthesized over billions of years as ultraviolet radiation broke down simpler molecules on the surface. There is even a more exotic possibility, that organic material from Saturn's moon Titan, which has a thick atmosphere rich in complex hydrocarbons, somehow made its way to Hyperion through processes we do not yet understand. The truth is, we simply do not know. And in science, the most exciting words are often "we do not know," because they mark the boundary between what we have discovered and what still awaits us. Let us talk about scale, because numbers alone cannot capture what Hyperion truly is. This moon measures roughly 270 kilometers across at its widest point. That sounds large until you realize you could fit it comfortably inside a small country. If you dropped Hyperion into the Mediterranean Sea, it would barely stretch from one coastline to the other. It is tiny by celestial standards, a fragment, a remnant. And yet this fragment contains mysteries that have occupied some of the finest minds in planetary science for decades. Its largest crater, a gaping wound in its surface, stretches nearly 120 kilometers across and plunges 10 kilometers deep. If you stood at the bottom of that crater, the walls would rise around you higher than Mount Everest, blocking out the stars, plunging you into a darkness broken only by the dim glow of Saturn on the horizon. The crater floor is covered in that strange reddish material, organic compounds mixed with dirty ice and rocky debris. Scattered across this alien landscape are boulders the size of buildings, thrown there by ancient impacts that would have shattered lesser worlds entirely. The crater walls are not smooth but riddled with smaller craters, impacts within impacts, a fractal record of violence stretching back billions of years. Some scientists believe that Hyperion was once part of a much larger moon, perhaps similar in size to Mimas or Enceladus. A catastrophic impact sometime in the distant past shattered this parent body, leaving behind only fragments. Hyperion might be the largest surviving piece of that ancient catastrophe, its strange shape a scar from a collision that rewrote the history of Saturn's moons. If this theory is correct, then somewhere in the rings of Saturn, somewhere among the countless particles of ice and dust, there might be other fragments of Hyperion's parent body. Pieces of an ancient world, ground down over billions of years into particles no bigger than snowflakes, circling endlessly around the ring giant. But why does Hyperion tumble so chaotically? This question drove mathematicians and physicists to develop new models of celestial mechanics. The answer involves resonance with Titan, Saturn's largest moon. Hyperion orbits Saturn in a pattern that brings it close to Titan regularly, and each encounter gives it a gravitational tug. But unlike stable resonances that lock moons into predictable patterns, the resonance between Hyperion and Titan amplifies tiny variations in Hyperion's rotation instead of dampening them. Imagine pushing a child on a swing. If you push at just the right moment, the swing goes higher and higher. The resonance between Hyperion and Titan works similarly, except instead of making the rotation bigger, it makes it more unpredictable. Every time Titan pulls on Hyperion, the chaos grows. Small changes become large changes. Predictability dissolves into randomness. This chaotic rotation has been going on for billions of years and will continue for billions more. Hyperion is trapped in a state of perpetual tumbling, a prisoner of gravitational forces it can never escape. In all the cosmos, it is one of the best examples of chaotic dynamics in a natural system. Physicists study it to understand chaos theory itself, using this distant moon as a laboratory for ideas that apply everywhere from weather patterns to stock markets. The Cassini mission gave us our best look at Hyperion during several flybys between 2005 and 2015. Each pass revealed new details, new mysteries, new questions. The closest approach came within about 500 kilometers of the surface, close enough to resolve features just a few dozen meters across. The images that came back were unlike anything from any other moon in the solar system. Those images showed a surface that looks almost organic in its texture, like a dried sponge or a piece of coral. The craters are sharper and deeper than craters on other moons, their edges well defined even after billions of years. This tells us that whatever process shapes Hyperion's surface works differently from the processes on other worlds. There is less weathering, less filling in of craters, less erosion of features. The moon is a museum of its own violent history, preserving impacts that would have been erased long ago on more geologically active worlds. Scientists noticed something else in those images. The darkest material on Hyperion's surface, those organic-rich deposits, seem to concentrate at the bottoms of craters. The pattern suggested that these compounds were somehow flowing downward, accumulating in low points over millions of years. But how could material flow on a world so cold that nitrogen itself would freeze solid? The answer might involve sublimation, the process where ice turns directly into vapor without melting first. On Hyperion, water-ice mixed with darker material gets hit by sunlight. The ice sublimates, carrying the darker particles with it. These particles settle in shadowed areas where there is no sunlight to move them again. Over billions of years, this slow migration of dark material creates the patterns we see today. It is a process happening in extreme slow motion, imperceptible on human timescales but transformative over the lifespan of a world. Right now, as you hear these words, particles of ancient organic material are drifting across Hyperion's surface, seeking the darkness of crater floors, continuing a journey that began before life on Earth crawled out of the oceans. The electrical charging of Hyperion raises practical concerns for future exploration. Any spacecraft sent to study this moon up close would need to account for the charged environment. Delicate instruments could be damaged by electrostatic discharge. Dust particles lifted by the charge could contaminate sensors and cameras. Even the simple act of landing might be complicated by electrical forces that do not exist on more conventional worlds. But these challenges also make Hyperion a fascinating target for future missions. A dedicated probe could study the charging process in detail, helping us understand how small bodies throughout the solar system interact with solar radiation and planetary magnetospheres. The organic compounds in those crater floors could be sampled and analyzed, potentially revealing secrets about the chemical evolution of the outer solar system. The chaotic rotation could be tracked precisely, providing data to test our models of gravitational dynamics. No such mission is currently planned. Hyperion remains on the edges of our attention, overshadowed by more famous moons like Titan and Enceladus with their potential for harboring life. But to those who study it, Hyperion represents something equally valuable, a window into processes that operate throughout the universe, made accessible by its proximity to our own small world. There is something haunting about Hyperion. It exists in eternal twilight, so far from the sun that our star appears as little more than a bright point of light. Saturn hangs in its sky, but because of that chaotic rotation, the planet seems to wander unpredictably across the heavens, sometimes visible for days, sometimes hidden beyond the horizon. The surface temperature hovers around 93 Kelvin, more than 180 degrees below 0 Celsius. At these temperatures, chemical reactions slow to a crawl. Changes happen over millions of years. Time itself seems to stretch into geological slowness. And yet this frozen, tumbling, electrically charged fragment of a shattered world has captured our imagination precisely because it refuses to be ordinary. In a solar system full of neat spheres and predictable orbits, Hyperion stands as a reminder that nature does not always follow our expectations. Sometimes the universe creates something strange, something that breaks the patterns, something that challenges us to expand our understanding of what is possible. The ancient Greeks named the Titans, and Hyperion was among them, the god of watchfulness and observation, father of the sun, the moon, and the dawn. It is fitting that this moon, discovered in 1848 by observers straining to see through primitive telescopes, carries the name of a god associated with watching. For over a century and a half, we have watched Hyperion, puzzled by its shape, confused by its motion, surprised by its properties. And Hyperion, in its own way, seems to watch back. That charged surface, those dark craters full of organic compounds, that unpredictable rotation that defies our calculations, all seem to pose questions that we are only beginning to know how to ask. What other secrets does this strange moon hold? What will we discover when we finally send a mission dedicated to unraveling its mysteries? The answer lies waiting in the darkness beyond Saturn's rings, tumbling slowly through the void, carrying charges that could spark against any visitor brave enough to approach. Hyperion keeps its secrets well. But secrets exist to be uncovered. And somewhere in the future, perhaps sooner than we imagine, human technology will return to that distant moon, and we will finally begin to understand what makes the sponge moon of Saturn one of the most remarkable objects ever discovered. Until then, Hyperion tumbles on, a cosmic enigma circling a ringed giant, electrically charged, organically stained, chaotically spinning through the endless night. It was here before us. It will remain long after we are gone. And in its strange, tortured form, it carries evidence of processes that shaped our solar system, clues to questions we have not yet thought to ask. The universe is vast beyond comprehension, filled with wonders that dwarf our imagination. But sometimes the most profound mysteries come in small packages. Sometimes a moon barely larger than a city holds secrets that could rewrite textbooks. Sometimes the strangest things in the cosmos are waiting just beyond the familiar, hidden in plain sight around a planet we have known about for thousands of years. Hyperion is one of those things. Small, strange, charged, chaotic, and utterly unlike anything else we have ever found. It demands our attention not because of what it might give us, but because of what it teaches us about the universe we inhabit. And that might be the most important thing of all. The story of Hyperion's discovery is itself a tale of persistence and obsession. In September 1848, two astronomers working independently on opposite sides of the Atlantic Ocean both spotted this tiny speck of light near Saturn within days of each other. William Cranch Bond, working at the Harvard College Observatory with his son George, detected the moon on September 16. Just 2 days later, William Lassell in England made the same discovery using his own telescope. The question of who deserved credit sparked a minor controversy in astronomical circles, one that was eventually resolved by giving both parties recognition. But consider what it meant to find Hyperion in 1848. These astronomers had no photography, no computers, no spacecraft. They sat in cold observatory domes, squinting through eyepieces at a point of light so faint that even slight atmospheric disturbance could make it vanish. They tracked its motion night after night, proving that it orbited Saturn rather than being a distant star. They calculated its orbital period using mathematics done by hand, filling pages with calculations that would take a modern computer microseconds to complete. What they could not know, what nobody would know for more than a century, was just how strange their discovery truly was. To them, Hyperion was simply another moon, the eighth discovered around Saturn, a small addition to humanity's map of the solar system. The tumbling rotation, the spongy surface, the electrical charge, the organic compounds, all of these revelations lay far in the future, waiting for technology that had not yet been imagined. This is how science often works. We make discoveries without understanding their significance. We collect data without knowing what questions it will eventually answer. The astronomers of 1848 gave us Hyperion. It took until the space age to reveal what they had actually found. The first spacecraft to visit Hyperion was Voyager 2 in 1981. The images it returned were grainy by modern standards, limited by the technology of the era and the vast distance the data had to travel. But even those early pictures showed something unexpected. Hyperion was not round. Its shape was so irregular that initial measurements of its size varied wildly depending on which angle was being photographed. Scientists described it as looking like a hamburger patty, a potato, a battered piece of debris. None of these comparisons captured its true strangeness, but all of them conveyed the essential point: this was not a typical moon. Voyager 2 also detected the chaotic rotation, though proving it mathematically would require years of additional observation. The spacecraft caught Hyperion in one orientation, but ground-based telescopes watching over subsequent months saw the moon present different faces at unexpected times. The pattern, or rather the complete absence of pattern, slowly became clear. Hyperion was not just irregularly shaped. It was irregularly moving. The Cassini-Huygens mission, launched in 1997 and arriving at Saturn in 2004, transformed our understanding of the entire Saturnian system. For 13 years, this spacecraft orbited Saturn, flying past its moons dozens of times, returning data that researchers are still analyzing today. Cassini's encounters with Hyperion were among the mission's most visually striking achievements. The closest approach came on September 26, 2005. As Cassini swept past at a distance of just 505 kilometers, its cameras captured images with resolution better than 30 meters per pixel. For the first time, humanity saw Hyperion in sharp detail. And what we saw was breathtaking. The surface looked like nothing else in the solar system. Those deep craters, with their sharp rims and dark floors, gave the moon an appearance almost biological in nature. Some observers compared it to a wasp nest, others to a dried coral reef, still others to the seed head of a lotus flower. The technical term for this texture is negative relief, meaning the craters are deeper relative to their width than craters on other bodies. On most worlds, crater floors are relatively flat, filled in by debris and geological processes over time. On Hyperion, the craters remain gaping pits, as if the moon lacks whatever processes smooth out surfaces elsewhere. The leading explanation involves Hyperion's low density. This moon is only about half as dense as water ice, making it one of the least dense objects of its size in the solar system. If you could somehow transport Hyperion to Earth and drop it in the ocean, it would float. That remarkable fact tells us that Hyperion is not solid. It must be riddled with voids and cavities, internal empty spaces that account for its low mass relative to its volume. Some estimates suggest that Hyperion might be as much as 40% empty space. Picture a structure like a frozen sponge, where ice and rock form a matrix around countless pockets of vacuum. When something impacts this porous surface, the energy goes into compacting the material directly beneath the impact rather than spreading outward to form a traditional crater. The result is those deep, sharp-edged pits that give Hyperion its distinctive appearance. This porosity also explains the electrical charging observed during Cassini's flyby. A solid surface can dissipate electrical charge relatively easily, conducting electrons across its face until equilibrium is reached. But a porous surface acts differently. Charge gets trapped in shadows and crevices. It accumulates in isolated patches that cannot easily discharge to their neighbors. Over time, as solar radiation and particles from Saturn's magnetosphere continue bombarding the surface, these isolated patches build up stronger and stronger charges. When Cassini flew past, it entered a region of space where some of this charge was escaping into the vacuum. The spacecraft detected a beam of electrons flowing outward from Hyperion, and instruments recorded a voltage potential difference between the moon and the surrounding space. In effect, Hyperion was acting like a static electricity generator, constantly charging and occasionally discharging as conditions allowed. This phenomenon has implications far beyond one small moon. Throughout the solar system, there are countless small bodies with irregular shapes and porous surfaces. Asteroids, comets, small moons, and fragments of debris all share some of Hyperion's characteristics. If Hyperion can develop significant electrical charging, so might these other objects. Future missions to asteroids and comets will need to account for the possibility that their targets are electrically charged in ways that could affect spacecraft operations. The organic compounds on Hyperion deserve deeper examination. When we say organic, we mean molecules built on chains of carbon atoms bonded with hydrogen, oxygen, nitrogen, and other elements. These molecules are called organic not because they come from living things but because they form the chemical basis for life as we know it. Carbon's ability to form complex chains and rings makes it uniquely suited for building the complicated molecules that biological processes require. On Hyperion, spectroscopic analysis has detected signatures consistent with carbon dioxide, hydrocarbons, and possibly more complex organic compounds. These materials appear concentrated in the darkest regions of the surface, particularly on crater floors where they are protected from direct solar radiation. The reddish color visible in these areas results from the way these compounds absorb and reflect light. Where did this material come from? The solar system's outer reaches are rich in organic compounds, delivered by comets that formed in the cold regions beyond Neptune where such molecules could survive intact. Hyperion, orbiting in Saturn's gravitational embrace, would have been bombarded by cometary material over billions of years. Each impact could have delivered fresh organic compounds, adding to the inventory on the surface. But there is another possibility, more intriguing and harder to prove. Saturn's largest moon, Titan, possesses a thick atmosphere filled with organic haze. This atmosphere is constantly producing complex hydrocarbons through chemical reactions powered by solar radiation. Some of this material escapes Titan's relatively weak gravity and spreads throughout the Saturnian system. Could organic compounds from Titan have made their way to Hyperion, coating its surface with material synthesized in another world's atmosphere? The chemistry would be fascinating if this hypothesis is correct. Titan's atmospheric chemistry produces molecules that do not form easily elsewhere, compounds like tholins that give the moon its orange color. If these same compounds exist on Hyperion, it would demonstrate a form of chemical connection between moons, a transfer of material that links distant worlds in unexpected ways. We do not have the data to confirm or reject this idea. It remains one of many hypotheses about Hyperion that await future missions to test. But it illustrates how this small moon connects to larger questions about the solar system's chemistry and the distribution of life's building blocks. Speaking of life, we should address the question directly. Could Hyperion harbor life? The honest answer is almost certainly not. The temperatures are too cold for any chemistry we know of to sustain biological processes. There is no liquid water, no energy source beyond feeble sunlight, no protection from radiation. By every measure we use to assess habitability, Hyperion fails. And yet, the presence of organic compounds in protected environments raises a different question. Not whether life exists on Hyperion now, but whether Hyperion preserves a record of chemistry that operated elsewhere. Those crater floors, shielded from radiation and unchanged for billions of years, might contain molecular fossils, evidence of chemical processes that occurred in the early solar system when conditions were different. This is speculative, but it points to Hyperion's potential scientific value. Even a lifeless world can teach us about the conditions under which life might arise. The organic compounds on Hyperion are not evidence of biology, but they are evidence of chemistry, chemistry that operates throughout the cosmos, chemistry that somewhere, sometime, under the right conditions, might make the leap from complex molecules to something we would recognize as alive. The chaotic rotation of Hyperion offers lessons that extend beyond astronomy into pure mathematics. Chaos theory, the study of systems sensitive to initial conditions, found one of its most elegant natural examples in this tumbling moon. Scientists studying chaos often use computer models or laboratory experiments to explore how small changes grow into large ones. Hyperion provides a natural laboratory operating at scales no human experiment can match. To understand why Hyperion tumbles chaotically while other moons do not, we need to think about energy dissipation. Most moons in the solar system rotate synchronously, keeping one face permanently turned toward their parent planet. Earth's moon does this, as do nearly all large moons throughout the solar system. They reach this state through tidal friction, a process where gravitational forces flex the moon's interior, generating heat that slowly drains energy from the rotation until only the most stable configuration remains. Hyperion never reached that stable state. Its irregular shape means that tidal forces do not act uniformly on it. Different parts of the moon experience different gravitational tugs depending on their position relative to Saturn. Add to this the regular gravitational kicks from Titan, and you get a system where energy cannot settle into a minimum. Instead, the energy sloshes around, driving rotational changes that feed back into the orbital dynamics, which in turn affect the rotation. The mathematics describing this system involves nonlinear differential equations that cannot be solved exactly. We can only approximate solutions using numerical methods, running simulations that step forward moment by moment to see how the system evolves. These simulations show that tiny changes in initial conditions lead to wildly different outcomes over time, the hallmark of chaotic behavior. What makes this significant is that Hyperion has been in this chaotic state for billions of years. Unlike chaotic systems on Earth that might operate for seconds or hours, Hyperion demonstrates chaos over geological time. It is proof that chaotic dynamics can persist indefinitely under the right conditions, neither settling into stability nor flying apart into destruction. For physicists and mathematicians, this matters because it expands our understanding of what is possible. Chaos is often associated with instability, with systems that quickly become unpredictable and uncontrollable. Hyperion shows that chaos can be a permanent state, a way of existing that some objects in the universe have maintained since the formation of the solar system. Let us return to the question of Hyperion's origin. The prevailing theory holds that Hyperion is a fragment of a larger body destroyed by impact. Several lines of evidence support this idea. First, Hyperion's irregular shape suggests it is not a primordial object that accreted gradually from the solar nebula. Primordial objects tend toward spherical shapes because gravity pulls material equally in all directions. Hyperion looks like a piece of something larger, torn off by violence. Second, Hyperion's orbit is consistent with formation through disruption. It orbits Saturn at a distance of about 1.5 million kilometers, in a 4:3 resonance with Titan. This means that for every 4 orbits Hyperion completes, Titan completes 3. Resonances like this are common in planetary systems and often indicate shared histories between the objects involved. Third, Hyperion's composition resembles that of other moons in the Saturnian system, suggesting a common origin from the same reservoir of material. If Hyperion were a captured object from elsewhere in the solar system, we might expect its composition to differ noticeably from local moons. Instead, it fits the pattern. The destruction of Hyperion's parent body would have been a catastrophic event. An impactor large enough and fast enough to shatter a moon would have released energy comparable to billions of nuclear weapons detonating simultaneously. The debris would have spread throughout the region, some falling into Saturn, some escaping into other orbits, some coalescing into the fragment we now call Hyperion. If this theory is correct, then other fragments might still exist, either as smaller moonlets that have escaped detection or as particles now incorporated into Saturn's rings. The search for these siblings of Hyperion continues, though the vastness of space and the smallness of the targets make discovery challenging. There is a certain melancholy in contemplating Hyperion as a survivor of destruction. This small moon, tumbling alone through the darkness, is all that remains of a larger world. Whatever processes shaped that parent body, whatever history it accumulated over billions of years, all of it was erased in a moment of cosmic violence. Only this fragment persists, carrying clues to a story we can never fully reconstruct. But perhaps that is the wrong way to think about it. Perhaps Hyperion should be seen not as a ruin but as a beginning. The destruction of its parent body created something new, something unique, something that has fascinated scientists for nearly 2 centuries. Without that ancient catastrophe, there would be no spongy surface, no chaotic tumbling, no electrical charging, no concentration of organics in darkened craters. The Hyperion we study today is a product of its violent birth, shaped by forces that continue to act on it even now. In this sense, Hyperion embodies a truth about the universe. Destruction and creation are not opposites but partners. Stars die to create the heavy elements that form planets. Galaxies collide to trigger new waves of star formation. Moons shatter to produce objects that defy our expectations. The cosmos is not static but dynamic, constantly remaking itself through processes that seem catastrophic on human scales but are simply the way things work on cosmic ones. As we continue exploring the solar system, Hyperion will remain an important reference point. It shows us what is possible at the margins, where small size and irregular shape lead to phenomena that larger, rounder worlds do not exhibit. Every discovery about Hyperion teaches us something applicable to other objects throughout the universe, from asteroids that might threaten Earth to moons around distant exoplanets that we have not yet detected. The next generation of telescopes and spacecraft will bring new tools to bear on these questions. The James Webb Space Telescope, already revolutionizing our view of the distant universe, can turn its infrared eyes toward Saturn's moons, detecting details in their surface compositions that earlier instruments could not resolve. Future missions to the outer solar system, whether dedicated to Saturn or passing through on their way elsewhere, might carry instruments specifically designed to study electrical charging and organic chemistry. And someday, perhaps within the lifetimes of people alive today, a dedicated mission might land on Hyperion itself. Such a mission would face extraordinary challenges. The chaotic rotation makes planning a landing sequence incredibly difficult, since you cannot predict which face of the moon will be oriented toward you at any given moment. The electrical charging might interfere with equipment in unpredictable ways. The porous surface might not provide stable footing for a lander, risking a slow sinking into the spongy material. But these challenges are not insurmountable. Engineers have solved harder problems when given sufficient motivation and resources. A Hyperion lander could carry instruments to sample the organic compounds in crater floors, testing hypotheses about their origin and composition. It could measure the electrical environment directly, characterizing the charging process in ways that remote observation cannot achieve. It could deploy seismic sensors to probe the internal structure, revealing just how porous this strange moon really is. Such a mission would transform Hyperion from a distant curiosity into a known world, a place with measured properties and catalogued features. The mysteries would not disappear, but they would become sharper, more focused, pointing toward specific questions that future research could address. Until that day comes, we watch from afar. Telescopes on Earth and in orbit continue monitoring Saturn and its moons. The data from Cassini, still being processed and analyzed years after the mission ended, continues yielding new insights. Theoretical models grow more sophisticated, incorporating new physics and better computational methods. And Hyperion tumbles on, indifferent to our attention, following gravitational laws that we have learned to describe even if we cannot fully predict their outcomes. It has existed for billions of years before humans evolved. It will continue existing for billions of years after our species is gone, whatever fate awaits us. Our observations and theories are momentary flickers in its long existence, brief interactions between a small moon and the curious minds that arose on a rocky planet deeper in the solar system. There is humility in that recognition. For all our technology, for all our ambition, we remain small creatures on a small world, reaching out with instruments and imagination to touch things vastly older and more enduring than ourselves. Hyperion does not need us to understand it. The understanding we seek is for our own benefit, to satisfy the curiosity that drives our species, to answer questions that we cannot help but ask. What makes Hyperion charged? Why does it tumble? Where did the organics come from? What happened to its parent body? These questions matter because we have decided they matter, because the human mind cannot rest easy with mysteries unexplained, because knowing things is what we do. And so we continue watching, continue studying, continue sending our machines into the darkness to bring back glimpses of worlds we will never personally touch. Hyperion rewards that effort with strangeness, with properties that challenge our assumptions, with data that forces us to think harder and deeper about how the universe works. That is the gift of places like Hyperion. They remind us that our theories are always incomplete, our knowledge always provisional, our understanding always subject to revision when new evidence arrives. The universe is under no obligation to match our expectations. Sometimes it presents us with objects so weird, so unlike anything we predicted, that we have no choice but to expand our mental models to accommodate them. Hyperion is one of those objects. A sponge in space, charged and tumbling, stained with ancient organic compounds, surviving from a catastrophe that erased its parent world. It is everything a moon should not be, and that is precisely why it deserves our attention. The silence of space surrounds it. No sound travels through the vacuum. The collisions that shaped its craters happened without noise, the electrical discharges flicker without thunder. It is a world of eternal quiet, where even the most violent events unfold in perfect silence. But in our observatories and laboratories, in our data centers and scientific journals, Hyperion speaks volumes. Every image, every spectrum, every measurement adds to a story that we are still learning to read. The story of a small moon with big secrets. The story of chaos and charge. Destruction and survival, chemistry and physics intertwining across billions of years, and perhaps that is the most profound lesson Hyperion offers us. Not the specific details of its composition or rotation, not the technical measurements of its charge or density, but the deeper truth that the universe remains full of surprises. We have explored our solar system for centuries, mapped its planets and catalogued its moons, sent robots to distant worlds and peered through telescopes at objects billions of kilometers away. And still, a small moon around Saturn can humble us with its strangeness. When future generations look back at our era of space exploration, they will see it as a time of beginnings. We took our first tentative steps beyond our home planet. We sent machines to every major world in our solar system. We gathered data that transformed our understanding of where we live and how it came to be. But they will also see how much we left undone, how many questions we raised without answering, how many mysteries we identified without solving. Hyperion will be among those unfinished stories. A moon that refused to behave as moons should, that challenged our models and rewarded our curiosity with deeper puzzles. The scientists who studied it did their best with the tools available. The spacecraft that visited it captured what they could in their brief flybys. But the full truth of Hyperion remains locked in its cratered surface, waiting for explorers who have not yet been born. This is how knowledge advances. Not in sudden leaps but in patient accumulation, each generation building on the work of those who came before, each discovery opening doors to rooms we did not know existed. The astronomers of 1848 could not have imagined Cassini. The engineers who built Cassini could not have predicted what it would find. And we, today, cannot foresee what future missions will reveal about this strange, charged, tumbling fragment of a shattered world. What we can do is keep looking. Keep asking questions. Keep sending our instruments into the darkness, searching for answers that will only lead to better questions. That is the nature of science, and it is the nature of the human spirit that drives it. We are curious creatures, unable to accept that some things are simply unknowable. Every mystery is a challenge. Every unexplained phenomenon is an invitation. Hyperion extends that invitation to us across 1 billion kilometers of empty space. It spins in chaos, charges in silence, holds its organic treasures in shadowed craters where sunlight never reaches. It asks nothing of us, demands nothing, expects nothing. But it offers everything to those willing to make the journey, whether through telescopes pointed at distant points of light or through spacecraft crossing the vast gulf between worlds. Somewhere out there, right now, as these words reach you, Hyperion continues its endless tumble. Saturn's pale light illuminates its strange surface. Particles from the solar wind strike its porous crust, adding imperceptibly to the charge that builds in its depths. Organic molecules sit frozen in crater floors, unchanged since before the dinosaurs walked the Earth, perhaps since before the Earth itself fully formed. It has been there all along, waiting. Waiting through the rise and fall of civilizations on our distant world. Waiting through ice ages and extinctions, through the emergence of consciousness and the invention of technology. Waiting for minds curious enough to notice it, instruments precise enough to study it, spirits bold enough to send machines across the solar system to photograph its tortured face. We noticed. We studied. We sent our machines. And what we found was a world unlike any other, a cosmic anomaly that refuses to fit our categories, a reminder that the universe will always be stranger and more wonderful than we imagine. That is the legacy of Hyperion. Not answers, but better questions. Not certainty, but deeper wonder. Not an ending, but an invitation to continue the journey of discovery that defines us as a species. The tumbling moon keeps its secrets still. But secrets, as we have learned, are simply truths that have not yet been uncovered. And somewhere in the future, perhaps sooner than we dare to hope, those secrets will begin to yield. Until then, we watch. We wonder. And we remember that even in the darkest reaches of space, even on the smallest and strangest of worlds, the universe has something to teach us. If only we are willing to learn.